Hey, welcome back. In this lecture, we will be looking at topological sort. We're going to both be looking at what it is and also how to find a topological sort on a graph using both a breadth-first search-based method and a depth-first search-based method. So we'll sort of be looking at both of those, and you get a feel for how each of those searches could contribute to an algorithmic solution, even though we've already seen a few breadth-first search ones already with Dijkstra's and Prim's. So a good example for illustrating what a topological sort is the use of a prerequisite graph. And so those of you who are local students know what I'm about to write up here very well. The remote students have had a little bit of exposure to this from the numbers I'm using, but these could be numbers for any university, so it doesn't really matter. I've just mentioned some of these courses from time to time. Consider CS225. I've always made mention to, in some discrete math course you probably took before coming here. That's our discrete math course, and 125 is our introduction to programming course. And I've made reference to that too when saying, oh, in 125, blah, 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 meaning in 125 or whatever intro to programming course you took, intro to computer science course you may have taken, then you learn certain things. And so both of those were prerequisites for this class. And so you presumably had some discrete math before taking this class, and you also presumably had some previous computer science experience before taking this class. And of course, anyone who's a local student has taken both of those courses here. If you're a remote student, you took them, wherever, or the equivalent wherever. There are, of course, other courses as well, too. 173 also is a prerequisite for CS273, which is our slightly more advanced theory course. And then the two of those together are prerequisites for CS373, which is our course that looks at algorithms in depth. And those of you who are remote students taking this to prepare for our remote master's program may end up taking that course at some point. And we've got other things as well. 125 is also a prerequisite for CS231, the Introduction to Architecture course, which leads to 232, which is the sort of Architecture 2 course. And that perhaps leads to 333. And you might say, okay, well, 275 also leads to 323, which is an operating systems course, which needs to know both about programming and data structures and slightly more advanced hardware or architecture. And then you might also say that, okay, 225 also, you can, after that, go ahead and take a graphics course, which would be 318. And so you've got a graph here of various course prerequisites where there are some dependencies and some courses where there aren't dependencies. But anyway, the idea here is you always, whenever you have a directed edge here, you always need to take the first course before taking the second, the source before the target. It wouldn't make any sense to say, well, I'm going to allow you to take 318, and then after that, you have to take 173. That wouldn't make any sense, which is why I've drawn that as a dotted line. You couldn't really have a prerequisite structure like that, or you'd never be able to start. If you had to take 173 to take 273, and 173 to take 225, and 225 to take 318, and 318 before 173, then you've got this cycle here that you're stuck with, and there's no starting point. So you can't, this dotted line edge, you can't really have edges like that in some sort of prerequisite structure. You need to have vertices like the 173 and 125 where there are no incoming edges. And that's where you can start. And then once you've taken those classes, that sort of now satisfies these edges, and now you could have taken 273 and 225 and 231 because you've taken their prerequisites. And once you take those classes, you could take these and so on. So the issue then is simply here one of prerequisites, and whenever you have any sort of dependencies, you could have a similar graph. If you're trying to build a house, these might be the various tasks involved in construction, and maybe you say, I need to lay the foundation before I can put up the walls. I need to put up the walls before I can put up, the roof. Or maybe you say, well, here's the foundation, and that's done before the walls, and the walls are put up before you put up the roof. And then once the roof's up, you can start doing the interior, because then you don't have to worry about it raining on the inside of the apartments or whatever. So if you're doing some project, you have jobs in certain order, and if one job has to come before the other one, then you can illustrate that as a directed edge, where here's the job that must come before, and there's the job that must come after. Where once you have the roof built and everything, you may say, well, you've got the plumbing and the electrical work, and maybe those can be done independently of each other. And so you could say, well, if that node represents the roof and walls being done, then you could do both the plumbing and the electrical work, and it wouldn't matter, which one you do first, or you can do them both at the same time or whatever. So you can, and I have no idea if that's accurate or not, but I'm not in construction, I'm in computer science. So if anyone knows that, oh, you can never do plumbing before electrical work, then I apologize. So you've got, the example hopefully illustrates my point. The idea here is, in general, you can have what is known as a directed acyclic graph. A graph that is both directed and has no cycles. And that's the idea here. It's a directed graph because you're saying the edges don't work in both directions. You definitely say, I need to do this before this. So you have a definite source and a definite target. And it's acyclic because of things like this dotted line edge up there that I said isn't really in the graph. You can't have cycles. It wouldn't make sense to say that you have a ring of vertices, each of which is dependent on the previous one, because then you could never start and never complete any of those jobs. And the 173, 225, 318 cycle illustrates that very nicely. That if each of those courses has the one before it as a prerequisite, then you could never take any of them, because you'd have, each one of them requires a course you haven't taken yet. And so such things, we have prerequisites for courses, or you have, jobs, a sequence of smaller jobs that make up a larger job, and certain ones need to be done before others, or those kinds of real-world situations can be modeled using this kind of a graph, a directed acyclic graph, where the directed edges go between something that needs to be done first and then the job that can't be completed until that earlier job is done. And that's where your directed edges will connect things. This has an abbreviation. It's commonly called a DAG for short, just from directed acyclic graph. And we have the notion on such a graph of something called a topological sort. I'm going to write here. We talk about the topological sort on a graph. It's only defined for a directed acyclic graph, only defined for DAG. If you have cycles in a directed graph, then you can't create a topological sort. And of course, we haven't explained what it is yet, but first I want to just establish that. If you have cycles, you can't create a topological sort. And furthermore, if you have an undirected graph, then the whole point of this kind of ceases to have meaning to begin with, because the whole point is going to be to list the vertices in an order that is consistent with the directed edges and the order of the tasks that they convey. And if you don't have any direction to these edges and there's no order defined by these edges, then the whole thing is meaningless anyway. So it only makes sense to do this for a directed graph, and it'll only work if it's a directed graph without cycles. And the goal here will be to list the vertices in some order such that for every directed edge, and so I just wrote it for every edge here, but it's for every directed edge because it's a directed graph. For every edge I, j, vi is listed before vertex j. So in other words, and I could have really written this edge as if I wanted to, vi, vj as well, if that would make things clearer. The idea is basically, for every edge in your graph, the source of that edge has to be listed before the target. So in the graph we looked at, we would, for example, need to have CS173 come before CS225 in the listing, because since there is an edge from CS170, and I'll do a full example in a moment, I'll go back to that other sheet. Since there's a full graph, or since there's an edge between CS173 and CS225, therefore CS173 needs to be listed before CS225. If you have a listing of the vertices in which CS225 appears before CS173, it's not a legal topological sort. If you have a listing where CS225 appears before CS125, it's not a legal topological sort. By virtue of having this setup, where both of those are sources of the 225 vertex, therefore 173 must be listed before 225, and 125 must be listed before 225. But now these two have nothing to do with each other. There's no edge between 173 and 125, so we can list those in either order. Which means topological sort is not necessarily unique. Just in this simple graph alone, I have two different topological sorts. I could have said 125, 173, 225, or I could have said 173, 125, 225. We don't care what order those two vertices appear in, as long as they both appear before 225. And so another way of describing this is when you list out all the vertices and then draw the edges between them, all your edges have to be going from left to right. Whoops. Which indeed, in this case, in both cases they are. Where if I listed 225 before either of those, then I'd be going from right to left, and I don't want to do that. So that's the idea of topological sort. And just by way of an example on the earlier graph, we can go ahead and put this back up and say, well, you could go ahead and say 173 could be listed, and then 125, and then 225 could be listed, and then say CS318. And then you could say, well, then 231 could be listed next, and then 232, and then 323, and then 333. And then now you may go back and take the theory and say 273, and then finally 373 could be taken once you've taken both 275 and 273. So here I had 10 vertices in this graph. I've listed out the 10 vertices, but in this case, 173 is listed before both 273 and 225. 125 is listed before both 225 and 231. 225 is listed before all of the 300 level courses it affects. 318, 373, and 323. 232 is listed after 231. 323 is listed after both 225 and 232, and so on. So everything's okay here with regards to our prerequisites. This is one possible topological sort on this graph. And there are others as well. You know, for example, I could have just taken those two courses and flipped them around, and it's still perfectly legal topological sort. I could have listed all the 100s, and then these, and then this one, and then all of those, and then that. So there's a number of ways to print these vertices out so that they satisfy the topological sort requirement. And what we're concerned with in this case today is finding one topological sort. And each of the ways we do things might find different topological sorts. We're just concerned with finding one of them. So let's consider a graph such as this. We could, of course, done the same thing with the other graph we were just dealing with, but a smaller graph will mean less time on the example, and we'll have time to finish this all in one lecture. So let's say we have 4 here, and then we have here 5, and 3 and 4 also point to 5, and then 4 and 5 point to 6. So we have 6 vertices here. And we can note 2 facts about a directed acyclic graph, of which this graph is one. For all DAGs, property 1, so both of these things are true for all DAGs, for all directed acyclic graphs. Firstly, there is some vertex with no entering edges. In this case, we have 2 of them, vertex 1 and vertex 2. In general, if we had no entering edges for any vertex, then we know we've got a cycle somewhere. I'm not going to prove that, but basically, if there's no cycles in the graph, there will be definitely one vertex somewhere that doesn't have any edges entering it, and that can be your start point. And if you have cycles, then there will be some vertex that has, you can still have, I could have just pointed 6 to 4. So it's possible to have a cycle 4, 6, 6, 4, and still have some vertices with no entering edges. But if you have a vertex, if you have no vertex that has no entering edges, if every vertex has some entering edges, you've got a cycle for sure somewhere, and it won't be a directed acyclic graph. So we know, like I said, I'm not going to worry about proving that, but this is true for directed acyclic graphs. The second property is, and this one's going to be a little easier to prove if you assume number one, if you remove that vertex, the one with no entering edges, and all its departing edges, you still have a directed acyclic graph, and one still applies. And if you assume one is true and you have this kind of a vertex with no entering edges, if I was to remove that and all the departing edges, so for example, if I was to remove vertex 1 and get rid of its 2 departing edges, what that would mean is, well, now, of course, I still had vertex 2, but notice now if I'm left with another graph that still has a vertex with no entering edges, 2. And so I still have a directed acyclic graph. Doing this could not possibly change that because, firstly, it's removing vertex 1 and those departing edges does not change it from being a graph to not being a graph. It's certainly still a graph. And furthermore, it doesn't suddenly magically make the edges undirected, so it's still a directed graph. And furthermore, removing edges cannot cause cycles. If there's no cycle to start with, then removing a particular edge is not going to suddenly create a cycle where there was none. Adding edges can create a cycle, possibly, but removing edges can't create a cycle. So if we had a graph that was both a graph and further a directed graph and still further a cyclic graph, removing a vertex and some edges is not going to change any of that. Whatever else it might do, it'll still be a graph, it'll still be a directed graph, it'll still be an acyclic graph. So if one applies for all directed acyclic graphs, then that means if you were to remove that no entering edges vertex and all its departing edges, there will definitely be another such vertex because it's still a directed acyclic graph. Now that vertex may have been there before, as was the case for 2. We removed 1, but we still had 2, which we could have picked the first time anyway. If I remove 2 and its entering edges, or its departing edges, now I've removed both vertices that were initially had no entering edges, but in the process now I've created a new one. Initially, 3 had 2 entering edges, but in the process of removing 1 and then removing 2, even though now we've chewed up both of the vertices we had available to us to select before, we've now in the process created a new no entering edges vertex. Just like you might say, well, I can't take 225 when I first get to U of I, but once I've taken a discrete math course like 173 and an introduction to CS course like 125, then now that I've taken those prerequisites, that sort of erases the 173 to 225 edge and the 125 to 225 edge, and now you can take 225. So for an example, you're basically saying for any course prerequisite structure, there's some course you can start at, and once you take that course, there will be some other course you can take. Because, if the prerequisite structure has no cycles, taking one of the courses doesn't suddenly produce a cycle in the prerequisite graph. So now that means there will be some other course you can go ahead and take. Some new course for which you've satisfied all the prerequisites, if any. And so we can use those two ideas to make up an algorithm that will let us find a topological sort. We can basically remove such vertices one by one. We will use the term of called integree here, where we say the integree is the number of entering edges and so what we're really looking for here, we're saying there is some vertex with integree equal to 0. And then if you remove that, there will be some other vertex with integree equal to 0. And if you remove that, and its departing edges, of course, there will be some other vertex with integree equal to 0. And if you remove that and its departing edges, you still have a directed acyclic graph. There'll be some other vertex with in degree equal to 0. And you keep doing that until you're out of vertices. If you indeed have a directed acyclic graph, then every time you remove an in degree 0 vertex, you will have another in degree 0 vertex you could find and remove at the next step until you have no vertices left at all. And so that suggests that that's certainly a viable way to find the topological sort, because if we're always removing a vertex, such as 1, and its departing edge before we remove the target, I had to remove 1 before 3 would have been presented as an option to remove. That means we will always remove the source of an edge before its target, and therefore the order in which we remove vertices from the graph would be a perfectly reasonable topological sort order, because I have to remove every edge source before the target of that edge, and I'll be doing that in this case, because I won't be able to remove the target until it's in degree 0, and it won't be in degree 0 until I've removed its source. So let me draw that graph back up. And we can have here 1 and 2, and here's 3, and here's 4, and here's 5, 6. And one way we can do this is to say, let's set up a table. Where I say here, I'm just going to write ID here for in degree, and this will be a K field, this will be a known. And once we've processed a vertex, we'll mark it known. The idea here will be, rather than actually removing the vertex from the graph, we can simply sort of mark it processed. And so at that point, those directed edges won't matter. We can mark those as well. And so if our graph class allowed it, we could then say, instead of removing the vertex and its directed edges, we'll just sort of mark them. And then what the goal will be, when a vertex, such as 3, has no entering edges that are unmarked, then at that point we've processed all the incoming edges. Basically, every time we process an entering edge, we'll mark it. And so when there are no unmarked edges left, it's the same as if we have removed the edges. The idea of marking the edges is the same as removing it, except this way we don't really need to remove it. And so saying we have no edges entering is sort of saying we have no unmarked edges entering. So what we can do is first traverse over the graph and find all the in degrees to start with. Our graph class happens to store that just within the vertex. We have a list of entering edges, and so we say, whenever you have an entering edge, then you have a vertex head as a list of entering edges, and we also store that information in the vertex. If you didn't have that stored, assuming you have an adjacency list representation, you're just reading off all the edges one by one in order v plus e time. So you could say, in that worst case, order v plus e time. If you have an adjacency list representation, you can read the in degrees simply by traversing over all the edges one by one and reading the 2 endpoints of each of those. You can then find out what the source and what the target is of that edge, and basically add 1 to each of these as you go. So that would remain 0, that would be 0. That would have an in degree of 2, of 2, of 3, and of 2. And certainly that total should equal the number of edges in the graph. And here we've got 4, 5, 6, 7, 8, 9, and that does indeed add to 9, so we're okay. And then each of these is unknown at this point. But the way we do that is we'd say, well, here we have an edge from 1 to 3, so we add 1 to 3's total, and then we have an edge from 2 to 3, so we add 1 more to 3's total, giving us 2. And we have here an edge from 3 to 5, so we'd have a 1 there, and an edge from 4 to 5, so we'd have a 2 there, and so on. So as we look at each edge, we could just start those all off at 0 and add those totals one by one until we arrive at the final answer. And traversing the adjacency list structure in that manner would take v plus e time. So the initialization here at most takes v plus e time. Once we've initialized it, so reading the in degrees is our initialization step. Once we've initialized things, then we simply say at each step, we're going to basically say we loop v times, and here we search the table for a vertex with in degree equal to 0 and known equal to 0, and then mark it and the departing edges by way of adjusting table. In other words, I search the table for a vertex with in degree equal to 0 and known equal to 0. And I find one right away, vertex 1. What I will do here is I'll say, well, that is known. And so that's how I mark the vertex. I say, okay, now this shouldn't be processed anymore. Otherwise, I'd keep picking 1 in every step. And the way I mark the departing edges here, I can, of course, mark them physically in my graph. What I can also do is in the table, when we say we want to adjust the table, our other concern here is saying, well, I need to adjust the in degrees of some of the other vertices. Specifically, if I was to remove 1, that would lower the in degree of vertex 3 by 1. It would also lower the in degree of vertex 5 by 1, because those are the neighbors of 1. So each of those should go down, this is 2. Each of those should go down by 1. And that's the sort of equivalent of marking the edges. We say each of those in degrees is decreased. And I just keep repeating that procedure. The second of 6 times through the loop, I look for another vertex with in degree equal to 0 and known equal to 0, and I find 2 this time. And I say, okay, mark that. And then what are the neighbors of 2, 3, and 4? So if I was to remove 2 and its departing edges from the graph, that would reduce the in degree of vertex 3 by 1, and it would reduce the in degree of vertex 4 by 1. And so the first vertex we processed was 1. The second vertex we processed was 2. Now I search the table for another vertex that has in degree 0 and known equal to 0, because I don't want to keep processing 1 and 2 all over again. And I'll say, well, vertex 3 has in degree 0 and a known equal to 0, so I can list that. I mark that known, and I say, what are the neighbors of 3? Well, they're 5 and 4, which means if I was to remove 3 and its departing edges, 5's in degree would go down by 1, and 4's in degree would go down by 1. And so that's the end of step 3. Step 4 says, once again, search the table for a vertex with in degree 0 and known equal to 0. There's only one such vertex, 4. So that's the next vertex we list. I mark 4, and I say, well, if 4 and its departing edges were to be erased, both 5 and 6, 4's neighbors, would have an in degree that decreases by 1. So 5's in degree decreases, and 6's in degree decreases. We search the table for another vertex of in degree 0 and known equal to 0, and we say, well, we keep looking. Hey, here's 1, here's 5. We mark that. That's next on our list. And if I was to delete 5 and its one departing edge, that would reduce the in degree of 6. And now I search the table for a vertex with in degree 0 and known equal to 0. This is my last time through the loop, and I find vertex 6. That's marked as 1. That's listed. There are no departing edges from 6, and we're all set. And here we have topological sort. Now, by pure coincidence, the order in which we did this happened to be the same order the vertices were listed in the table. But if the vertices had been listed in a different order in the table, we would have proceeded in a very similar manner. We could have perhaps picked 2 before 1, but we're not going to be able to pick 3 before both 1 and 2 are gone. We won't be able to pick 4 until 3 is gone. We won't be able to pick 5 before 4 is gone, and we won't be able to pick 6 before 5 is gone. And so there's only 2 possible topological sorts in this graph, the one we picked, or 2, 1, 3, 4, 5, 6. But it has nothing to do with the order of the numbers. That just by coincidence happens to be the order in which things turned out. The relevant part is the edges, and so by coincidence I've got my earlier numbers for the earlier vertices and so on. So, the question here is, what's the running time of this procedure? And the answer is, well, there's 2 components to this. We have a table search. We want to search the table for a vertex with in degree equal to 0 and known equal to 0. And in the worst case, that search can take order v time. In the beginning of the algorithm, we were very lucky. I'm going to put this back in a moment. In the beginning of the algorithm, we were very lucky, and we said, well, hey, look, right at the very start of the table, we have a vertex of in degree 0 and known equal to 0. By the end of the algorithm, we're having to search down the entire table to get to that point. And so overall, the worst search will be v. Overall, depending on how we proceed with our search, we may have to do a little less searching or a little more. But this was the ideal way to set up the search, where every subsequent vertex was we found it as early as possible, and it would still require a v search plus a v minus 1 plus a v minus 2 plus a v minus 3, so on and so forth, and that would be v squared. So the fact that sometimes we only have to search too far in the table, and we only have to search all the way to the bottom of the table, some of the searches doesn't make any difference. The worst case table search is v, and so overall, searching we have v steps. The worst case is v. Searching takes order v squared time. And the fact that we only had to search the first entry in the table the first time, and the second time we had to look down 2 entries, and the third time we had to look down 3 entries, and so on, just means it's v squared over 2. You have a search time of 1 in the first step, and 2 in the second step, and 3 in the third step, and 4 in the fourth step, and 5 in the fifth step, and 1 plus 2 plus 3 plus 4 plus 5 plus blah, 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 plus n is going to equal n squared over 2, roughly. So don't worry about that. That's just sort of the more in-depth math. The issue here that you should view this as is basically your worst case search is order v time, and you have v steps, so that's v squared time searching total in the worst case. And then we say, what about updates? And when we deal with updates, we basically say, given a vertex, reversed list of neighbors, and that was why we said we'll assume the adjacency list implementation, because that's really nice in this case. So assuming the adjacency list implementation, we're traversing the list of neighbors, and for each neighbor, we update the in degree in the table. And we're going to assume that's constant time. That either we're actually, this table is really a collection of our actual vertex nodes, or we have some way of going directly from vertex to a table entry. If it takes forever to go from the vertex to a table entry, if we say, okay, 3 is a neighbor of 1, and now let's take some large chunk of time to find 3 in the table and reduce its in degree from 2 to 1, then yes, this whole thing would take longer. But we'll assume that we've got that set up quickly, that either we have the vertex directly and that's where we're storing these things, or else that somehow we've got maybe a table key built into the vertex, and we use that to look up vertex 3 in the table, or something like that. We'll assume some convenient setup where we have the ability to go from vertex to table entry and back conveniently. And so what we've got then is that updating is simply a matter of saying, well, once I know 3 is a neighbor, I jump to that table entry and I change that. That's constant time per edge, and therefore this would be order E total. And so your whole time here is going to be order V squared plus E, which is equivalent to order V squared, even for a very dense graph, because E would be equal to V squared. So if we're just going to search, kind of use this brute force table search method, the time is dominated by your search time. Even if you have a very small number of edges, heck, even if you have no edges whatsoever, though then I guess it wouldn't be a directed acyclic. Well, I technically could be considered one. If you have all the vertices, no edges, there are no cycles, you just you'll kind of traverse down the vertices one by one. It'll still take order V squared time to do that overall, and there just won't ever be any neighbors and any in degrees to change. They'll all be in degree 0 to start with. So the search time here is what dominates this. So we say, well, can we do better than order v squared time? And indeed we can. And the way to try and beat that time is to consider what we're doing here and to recognize this is sort of a breadth-first search approach in the sense that for every vertex we latch onto, we look at all its neighbors at once and deal with them. So when I say it's time to process 1, I reduce the integrity of all its neighbors at once. When it's time to process 2, I reduce the integrity of all its neighbors at once. I don't wait till later in the algorithm to reduce the integrity of 4. When I reduce the integrity of 3, I also reduce the integrity of 4 when it's processing 2. When I process 3, I will reduce the integries of both 5 and 4 at that time. But we're throwing an important piece of information away here, and this is what's causing our problems. We're having to search the table for a vertex with in degree 0 and the known field equal to 0. However, there's times we know the vertex is in degree 0. When I adjust the table, for example, when I've already removed 1 and the in degree of 3 had changed from 2 to 1, and then I was processing 2 and the in degree of 3 changed from 1 to 0, well, at that point, I know the in degree of 3 is 0. I've just done a subtraction. I can check right then and there and say, hey, look, 3's in degree is now 0 because of this last subtraction. I had processed 1 previously, and now I'm processing 2 as well, and that now at this point that leaves 3 without any incoming edges, without any entering edges. And so if we did something about that at that time, it would mean I don't have to search for 3 later on. If I could somehow store 3 in some collection of 0 in degree vertices, such as a Q, then I don't need to search later on. I simply say, well, whenever anything becomes in degree 0, we'll stick it in a Q. And then rather than search the table, we simply day Q a vertex. So let's use that strategy and start this whole thing all over again. Continue here. Here we got 1, 2, 3, 5, 4, 2 points to 4, 1 points to 5, 4 points to 5, and both of them point to 6. And we've got here the vertex and the in degree. And we don't really even need a known field in this case. So that wouldn't be even necessary, and I'll explain why in a moment. Do our initialization, which we said before was order v plus e time in the worst case to do the initialization of traversing the adjacency list structure and finding out all the initial in degrees. And what we'll do is as we do that, I should even say after we do this, we take order v time, traverse table, add in degree 0 vertices to a queue. So we'll say here, here's our processing queue, and let me go ahead and add 2 and 1 to that processing queue. So who cares what order we traverse the table in? I'm just going to add them in that order. So what we have now is we have a table of in degrees for these vertices, and we have a queue of all the vertices that have in degree 0. And now at each step, we'll simply day queue vertex, and we will process vertex as before. Namely, we will reduce the in degree of all its neighbors. And we'll also have to on-queue those neighbors. Or I'm going to rewrite this. I'll describe the algorithm and then I'll rewrite it all later on because I'm running out of room here on this page. What we will do here is say, well, if I day Q2, and the order things appear in the queue will be the order of their topological sort, so now 2 is the first vertex for topological sort. We say, if I were to remove 2, and its departing edges, I don't really need to remove it, but I can at least explore what would happen. That would reduce the integrees of 3 and 4 by 1. So I go ahead and reduce those by 1. And since neither of them became 0, I don't enter them in the queue yet. This was a mistake down here. So now I day Q1, and that's my next vertex listed. And when I day Q1, 3 should be reduced because there's departing edges from 1 to 3 and from 1 to 5. 3 has an in-degree reduced, and because it's reduced to 0, I add that to the queue. 5 is also reduced, but it's not reduced to 0, so I don't add that to the queue. Now, I day Q3, and I say what are its departing edges, 5 and 4. 4 gets reduced by 1, and since that's 0, that gets added to the queue. 5 gets reduced by 1, but that's not 0, so I don't add it to the queue. We day Q again, and we say, well, what are the departing edges of 4? 5 and 6. 6 gets reduced by 1, but that doesn't equal 0, so I don't add it to the queue. 5 gets reduced by 1, and that does equal 0, so I do add it to the queue. And then I day Q5, and I say the neighbor of 5 is 6. That gets reduced by 1, and since that's 0, that'll get added to the queue. And then finally I day Q6, and 6 has no neighbors, so we're done. So the idea here was, when I did my loop v times, I would day Q a vertex and process it as before by way of what I meant there was, we look at its neighbors and decrease their in-degrees. But whenever the neighbor has an in-degree of 0, then we'll on-queue it. And so this is sort of our loop in this case. We'll say here, we loop v times. The loop says day Q vertex, and we'll call it v. Decrease the in-degree of all these neighbors by 1. And this was just as before. That's exactly what we did in the previous algorithm. But now, a neighbor which now has in-degree equal to 0, on-queue it. So that's how this will work now. Instead of searching, we do a day queue of the vertex, and this is going to be constant time rather than order v time. We decrease the in-degree of all the neighbors, and this was order e over the life of the algorithm, and we talked about that before. And then any neighbor which now has in-degree equals 0, on-queue it. And what this will do is, over the life of the algorithm, you'll on-queue each of these. So this will be now order v over the life of the algorithm. So no matter, whenever you day queue one vertex, that's going to be constant time. And so v times, we do that, because we loop v times, that will be order v. Whenever we're processing each edge here, so over the life of the algorithm, that's order e time, as we talked about earlier. And then, in this case now, we're on-queuing each vertex. We don't know which vertex is on-queued at which step. Some steps we may not on-queue any vertices. Some steps we may on-queue, 3 or 4 vertices. So we can't really say, well, at every step this is what happens, but we will say, over the life of the algorithm, every vertex gets on-queued exactly once. And so that's going to be order v over the life of the algorithm. This part's order e over the life of the algorithm. This is constant time each step, and so order v over the life of the algorithm. And so the total running time here is v plus e. Which for dense graphs is just as bad as before. It'll be order v squared time if the number of edges is about v squared. But for sparse graphs, this will be much better than before, because now instead of being order v squared time, this is v plus e. And so that's that result there. Now, it's also possible to solve this using a depth-first strategy. And the way we're going to solve this using a depth-first strategy, if I can put the graph back on, is to take note of an interesting fact, which is that, let's say I want to number these vertices, which of course I'm going to end up numbering them, 1 through 6. Let me actually, I'll leave it like this. I want to number these vertices in the order in which I want to have them in topological sort. What I know for sure is that a given vertex will definitely have a higher number than all of its preceding vertices. That is, whatever position, for example, that 5 is supposed to have in the final list. I know that its incoming edges, namely 1, 3, and 4, the sources of those incoming edges will have lower numbers, which is why it's nicer if, let me quickly redo this. Same exact graph, but so we don't, I'm just going to rename these letters. So we have here A, B, E, D, C, and then both of these are F. So if it turns out that F is the 6th vertex, which it's going to be, what we know for sure then is that everything that leads to F would have to have a lower position number if this is going to be a legal topological sort. If E is going to be the 5th vertex, which we know it will be, then everything leading to E is going to have a lower number. And what that tells us is that if we are sort of, in a sense, doing a post-order traversal of this graph, of course we can't exactly do post-order because it's not a tree, but if somehow we are marking a vertex after marking all of its neighbors, then what we could do is sort of count backwards and say, what I will do, for example, from C is make sure to mark E and D with their position number. Once E and D are marked, then if I'm giving position numbers in reverse order, we have 6 vertices here, there'll be some vertex of position 1, some vertex at position 2 in the topological sort, some vertex at position 3, some vertex at position 4, some vertex at position 5, and some vertex at position 6. And never mind what vertex is where, all I know is, say from vertex C, as long as I mark E and D with a position number before I mark C with a position number, then if I'm counting backwards, I'm okay. I can say I'll always assign these numbers in reverse order, and what I can do then is say, well, I won't assign C until I've assigned all of its neighbors. And that way all the neighbors are guaranteed to have larger numbers than C gets, which is exactly what we want. Likewise, I won't assign A until I've assigned numbers to C and E, and so therefore I guarantee, if I'm counting backwards, that C and E get larger numbers than A does. And I will definitely I won't assign B until I've assigned both C and D, and therefore I know C and D get larger numbers than B does. So we can make things work in that fashion, and the way we will accomplish this is we can basically use depth first search. But what we'll do with depth first search is we use the post-visit idea, where we had talked about visitation in these algorithms. And what I can say is, let's kind of put the depth first search idea again, but we'll have one key piece of information before that. So we sort of had our depth first search wrapper here that we had done before. And here we have our graph. And before we had said, for all V in your graph, your mark is equal to false. And then for all the V in the graph, if V mark is false or if it's 0, then do a depth first search on V. And that had been sort of our wrapper function. We had sort of said, well, set things up this way, where we had our list, we made sure all the vertices were false, and then we had some list of vertices. Maybe we have here the vertices in the list 3, 5, 1, 2, 6, and 4. And we'd say, well, start running a depth first search here. And if running a depth first search starting here happens to mark all the vertices, then as we traverse down the list, we won't find any unmarked ones. But if running a depth first search from 3 marks only 3, 4, 5, and 6, then as we continue traversing down with this loop, we'll say, okay, well, 3 wasn't marked, so we run depth first search on that, and that marks those. and then 5 was already marked, but 1 wasn't, so we'd run depth first search again off of 1, and that was how we generated that depth first spanning forest. And the same idea applies here. So this is exactly what we talked about before. What we're going to have is one extra piece of information here where we'll sort of say number equals, and that the lines around V are the cardinality, the size of V. We haven't really used that formal notation, but the book says that, and this, just so you know what I mean, the size of the graph is generally taken to be the size of the vertex set, and that would be formally how you notate the size of the vertex set. We've just been saying V plus E. What we really mean, the cardinality V plus the cardinality V. The number of vertices plus the number of edges, for example, when we talk about running times. So everything we did here really should have those lines around these to indicate we don't want the set, we want the size of the set. But in informal notation, it's not necessary. So that's the only thing we've added in the wrapper. And then for depth first search itself, actually I should have gone ahead and passed in the graph here as well. So let me say we have depth first search, pass in the graph, and the relevant vertex, just to be consistent with what I wrote last time. And what I have then here is we say, well, given the graph and your vertex, you say V mark equals true, and you say for all neighbors W of V, if W mark is false, then do a depth first search on this graph passing in W. So that's exactly what we had before. Now the new stuff says, this is sort of our Constantine post visit, we say v.number equals whatever the number value is. And then we can say number minus minus. That is, to the depth first search we talked about last time, we then say, once we're done looking at all of these neighbors, then we'll assign V. We started out with this value of number, and we can sort of treat this as sort of a global. We have to code it differently, but from an algorithmic standpoint, hopefully it's clear what I'm talking about. This is something that is accessible in all the depth first search calls, and we say that number starts out being the number of vertices, and then every time we've looked at all the neighbors of a vertex, we'll then say, well, go ahead and assign that number to the vertex and then decrease number by 1. So when we have 6 vertices, the first vertex we actually assign gets 6. Then we decrease that to 5, and the next vertex gets 5. And we decrease it to 4, and the next vertex gets 4, and so on. So if we come back to the original diagram, what we can do here is we can say, well, I'll go ahead and start at C, and from there I can traverse to E, and from there I can traverse to F. And from F I have, here's my number. From F I have no neighbors to explore, so I assign 6 to F and decrease that to 5. From E I have no more neighbors to explore, so I assign 5 to E and decrease that to 4. From C I have one more neighbor to explore, and that's D, and from there I have no unmarked neighbors. So I assign 4 there and decrease that to 3. From C, I have no more neighbors to explore, so I assign 3 to that and decrease that to 2. And now I need to start over with the traversal, and I can say, well, starting at B, there's no unmarked neighbors, and so that's 2, decrease that to 1. And then starting at A, there are no unmarked neighbors, so mark that as 1 and decrease that to 0. So here I had a depth first spanning forest of 3 different trees, one of 4 nodes, one of 1 node, the other of 1 node. If I had chosen instead to, for example, start with A, I could have done a similar thing up here. I could have said A goes to C, goes to D, goes to E, goes to F, and then we'd say from F there are no values, no more neighbors, so I mark that as 6. From E there are no more neighbors. From D there are no more neighbors. From C there are no more neighbors that are unmarked, of course. From A there are no more unmarked neighbors, and then we'd start again with B and mark that 1. So 2 different depth first searches, producing 2 different depth first spanning forests, but in both cases the numbering is a legal topological sort. And the reason that works is because we're always saying before you mark a vertex with a lower number, since you're numbering from high to low, the vertices that are marked first always have higher numbers. And since you mark a vertex after marking all its neighbors, for example, you mark 3 after marking E and D, you guarantee the neighbors always have higher marks than you. And that's what you want because you want your neighbors to have later positions in the collection than you do. And so then here the topological sort is B, A, C, D, E, F, and here it's A, B, C, D, E, F. And that's it. And of course, that's just order V plus E time because that's depth first search. And so we simply say that's the same time as depth first search because those two lines are constant time, and so that we said it was order V plus E, assuming that our post visit was constant time. And this is done once, and that's constant time. So the stuff we've added hasn't significantly changed the running time of depth first search. And so that said, that's the end of topological sort. We will talk a little bit more about a few more graph algorithms in the next few lectures. But other than that, we're done. So I'll see you next time, and take care.